Before Mercury became the silent, scorched world we see today, something catastrophic happened. Not a small impact, not a simple crater, but a collision so violent it reshaped an entire planet. On one side of Mercury lies a vast scar stretching over 1,500 kilometers wide, the Caloris Basin. A crater so enormous that it could swallow entire continents, a structure formed in the early chaos of the solar system, when planets were still being built and destroyed. But the impact didn't just leave a hole. It sent shockwaves through the entire planet. On the opposite side of Mercury, the surface is shattered into strange, chaotic terrain, as if the planet itself trembled from the force of that ancient collision. So what hit Mercury hard enough to do this? How powerful was the impact? And why did it leave marks on both sides of the planet? In this video from Stellar Depth, we uncover the story of Mercury's greatest scar, the Caloris Basin, and the violent moment that changed the smallest planet in our solar system forever. When we picture Mercury, the first images that often come to mind are of a small, scorched world racing around the sun. A planet so close to our star that daytime temperatures soar above 430 degrees Celsius, while the night side freezes to nearly minus 180 degrees. A world with no atmosphere to protect it, no oceans, no clouds, and no life as far as we know. At first glance, Mercury might seem simple, just a gray, cratered rock drifting through space. But the closer scientists looked, the stranger Mercury became, because hidden across its battered surface are clues to a violent history, clues that tell a story of unimaginable impacts, planetary shockwaves, and events powerful enough to reshape the entire world. And nowhere is that story more dramatic than in a massive scar known as the Caloris Basin. To understand why the Caloris Basin exists, we first need to understand the world it struck. Mercury is the smallest planet in our solar system, only slightly larger than Earth's moon. Its diameter is just under 4,900 kilometers. Yet despite its small size, Mercury is incredibly dense. In fact, after Earth, it is the second densest planet in the solar system. That density comes from something remarkable. Mercury has an enormous iron core. Scientists believe that the planet's metallic core takes up nearly 85% of its radius. That means most of Mercury is essentially a giant ball of metal surrounded by a thin, rocky crust. This strange structure hints that Mercury may have suffered a catastrophic event early in its history, possibly even a collision large enough to strip away much of its original mantle. But that is only part of the story. Billions of years ago, the inner solar system was a chaotic and violent place. Planets were still forming. Asteroids and protoplanets were constantly colliding. Massive impacts were common, and the surfaces of young planets were repeatedly reshaped by incoming objects traveling tens of kilometers per second. Mercury, being the closest planet to the Sun, existed in one of the most dangerous neighborhoods of the early solar system. And it shows. If you could hover above Mercury today and look down, you would see a surface covered in craters of every size imaginable. Some are small pits only a few meters across. Others stretch for hundreds of kilometers. Each one marks a collision. Each one tells a story of something slamming into the planet at incredible speed. But among all these scars, one stands above the rest. the Caloris Basin. It is one of the largest impact structures in the entire solar system. The basin measures roughly 1,550 kilometers across, large enough that if it existed on Earth, it would stretch from New York to Denver. Its rim forms a massive circular ring of mountains, towering several kilometers high. Inside the basin, the terrain is relatively smoother but still filled with fractures, ridges, and ancient lava plains. The name Caloris comes from the Latin word for heat, and the name is fitting, because the basin sits near Mercury's equator, where the sun's heat is especially intense. Temperatures there can become some of the highest anywhere on the planet, but the heat we see today is nothing compared to the heat that once formed it. The Caloris Basin was born in an instant of unimaginable violence. Scientists estimate that the object responsible for this impact may have been around 100 kilometers across, roughly the size of a small asteroid or dwarf mountain range. When it struck Mercury billions of years ago, it would have been traveling at speeds of more than 40 kilometers per second. To put that into perspective, that is over 140,000 kilometers per hour. At those speeds, the energy released is beyond comprehension. When the asteroid collided with Mercury, it did not simply punch a hole in the surface. The impact released energy equivalent to millions of nuclear bombs detonating at once. Rock vaporized instantly. The crust melted. Shockwaves rippled outward in all directions, fracturing the surface and throwing massive amounts of debris high above the planet. The impact blasted out an enormous cavity in the crust. Then, as the molten rock collapsed back inward, towering rings of mountains formed around the basin's edge. But the effects did not stop there. The shock waves from the collision traveled through Mercury's entire interior. Imagine striking a bell with a hammer. The vibrations travel through the metal, emerging on the opposite side. Something similar happened to Mercury. The seismic waves generated by the Caloris impact raced through the planet's mantle and core, eventually converging on the opposite side of the world. When those waves met, they had nowhere left to go. The energy focused into one region of Mercury's surface, causing the ground to buckle, crack, and collapse into a bizarre landscape now known as the Weird Terrain. But scientists would not discover that strange terrain or fully understand the Caloris Basin until centuries later. For most of human history, Mercury was simply a bright point of light in the sky. It appears close to the sun and is often difficult to observe. Ancient civilizations saw it as a wandering star, sometimes appearing at dawn, sometimes at dusk. Even with early telescopes, Mercury remained mysterious. Its small size and proximity to the sun made detailed observation extremely difficult. Unlike the Moon or Mars, its surface could not easily be mapped from Earth. For a long time, scientists knew almost nothing about Mercury's geology. That began to change in the 20th century. In the 1960s and early 1970s, space exploration had reached a point where spacecraft could finally travel to the inner planets. For the first time, humanity had the technology to send robotic explorers close to Mercury. The mission that would reveal Mercury's secrets was called Mariner 10. Launched by NASA in 1973, Mariner 10 became the first spacecraft ever to visit Mercury. The journey itself was an incredible achievement. Engineers used a gravitational slingshot around Venus to redirect the spacecraft toward Mercury, something never attempted before. When Mariner 10 finally flew past the planet in 1974, it began sending back images that stunned scientists. The surface looked surprisingly similar to the Moon, gray, heavily cratered, and ancient. But then, something enormous appeared in the photographs. A gigantic circular structure stretching across the surface. A basin so vast that it dwarfed nearly every other crater on the planet. This was the Caloris Basin. The discovery immediately captured the attention of planetary scientists. Not only was the basin massive, but the surrounding terrain showed signs of enormous tectonic forces. Ridges, fractures, and lava plains suggested that the impact had triggered geological changes across huge regions of Mercury's crust. Even more puzzling was what appeared on the opposite side of the planet. When Mariner 10 mapped the far hemisphere, scientists noticed a strange region where the terrain looked shattered and chaotic. Instead of smooth plains or regular craters, the surface appeared twisted, folded, and broken into bizarre patterns. At first, researchers could not explain it. But eventually, a theory began to emerge. Could it be possible that the Caloris impact was so powerful that its shockwaves traveled through the entire planet and erupted on the opposite side? If that were true, the Caloris Basin was not just a crater. It was evidence of one of the most powerful impacts ever recorded in the solar system. Yet Mariner 10 could only see about 45% of Mercury's surface. Half the planet remained hidden. For decades, the full story of the Caloris Basin remained incomplete. Scientists knew the basin was enormous. They suspected it had reshaped Mercury's crust, but many of its secrets were still waiting to be discovered. And it would take another spacecraft, decades later, to finally reveal what really happened on that distant, battered world. Because the Caloris Basin was not just an ancient scar. It was the key to understanding Mercury's violent past, and how the smallest planet in the solar system survived one of the most catastrophic impacts imaginable. Long before Mercury became the quiet, silent world we see today, the inner solar system was a place of chaos. 4.5 billion years ago, the planets were still forming. Vast clouds of dust and rock circled the newborn sun. Pieces of matter collided constantly, sometimes gently merging together, sometimes smashing apart in violent explosions. Asteroids, protoplanets, and massive fragments drifted through space like cosmic shrapnel. The early solar system was not peaceful. It was a shooting gallery. And Mercury, sitting closest to the Sun, existed in one of the most dangerous regions of all. At that time, the young planet's surface was still hot and unstable. Its crust had only recently begun to solidify. Beneath that thin outer shell, molten rock churned deep inside the planet. Mercury was still shaping itself. Then one day, something appeared in its path. A massive asteroid, possibly more than 100 kilometers wide, was racing through the inner solar system. Unlike modern asteroids that follow stable orbits, early solar system objects were constantly being pulled and redirected by the gravity of growing planets. Their paths were unpredictable. This particular object may have originated from the inner asteroid belt or from leftover planetary debris scattered during the formation of the terrestrial planets. Wherever it came from, its trajectory placed it directly on a collision course with Mercury. At speeds of 40 to 50 kilometers per second, the asteroid was moving faster than any aircraft, missile, or spacecraft humanity has ever built. But in space, those speeds were normal. Mercury had no atmosphere to slow the object down, no air to burn it up, no clouds, no winds, no protective layers. Nothing stood between Mercury and the incoming rock. As the asteroid approached, the planet's gravity pulled it even faster. Within seconds, the distance between them vanished, and then, impact. The moment of collision released an amount of energy almost impossible to imagine. The asteroid struck the surface with the force of trillions of tons of TNT. For an instant, the temperature at the impact site became hotter than the surface of the sun. The rock beneath the asteroid did not simply crack, it vaporized. A blinding explosion erupted across Mercury's surface. The asteroid itself was destroyed instantly, transformed into superheated plasma and molten debris. The surrounding crust melted and blasted outward in all directions. A massive shockwave spread through the ground. The force of the collision excavated an enormous cavity in Mercury's crust, hundreds of kilometers deep and more than 1,000 kilometers wide. But the explosion did not stop at the surface. The shockwave traveled downward through the planet's crust and into the mantle. Imagine striking a massive metal bell with a hammer. The vibrations move through the entire structure. That is what happened to Mercury. The energy from the impact surged through the planet like a seismic tsunami. Meanwhile, above the surface, a towering cloud of molten rock and vapor shot high into space. Some debris traveled thousands of kilometers before falling back to the surface. Some of it escaped Mercury's weak gravity entirely. For a brief moment, Mercury may have looked like a glowing, molten world again, its surface illuminated by streams of falling debris. But the most dramatic transformation was happening at the impact site itself. As the initial explosion settled, gravity began pulling the shattered crust back towards the center of the newly formed crater. This collapse created massive rings of mountains around the basin. These rings formed like ripples frozen in stone. Gigantic blocks of crust lifted upward, forming cliffs and ridges several kilometers high. These features still exist today. They form the mountainous rim surrounding the Caloris Basin. Inside the basin, the surface was completely reshaped. Molten rock flooded the interior, filling the deepest parts of the crater and creating smoother plains across the basin floor. Over time, this lava cooled and solidified, forming the relatively flat interior region scientists observe today. But the impact had effects far beyond the basin itself. The energy traveling through Mercury's interior continued racing across the planet. Within minutes, the seismic waves reached the opposite side of the world. There, something extraordinary happened. The shock waves converged. Just like ocean waves focusing on a shoreline, the seismic energy from the Caloris impact gathered at one specific region on Mercury's far side. When the waves met, they violently disrupted the surface. The crust buckled, mountains collapsed, cracks tore through the ground. Instead of forming a crater, the energy shattered the landscape into a chaotic maze of ridges, valleys, and broken hills. This strange region is now known as Mercury's weird terrain. Even today, it remains one of the most unusual geological formations in the solar system. The ground there looks twisted and shattered, as if the planet itself had been violently shaken from within. And, in a way, it was. The Caloris impact was not just a surface event. It was a planetary shock. The collision may even have affected Mercury's internal structure. Some scientists believe the impact could have temporarily altered the planet's rotation or triggered massive volcanic activity in the surrounding regions. Evidence of this may still exist in the lava plains that extend outward from the basin. Over millions of years, molten material from deep inside Mercury may have risen to the surface, filling cracks created by the impact. These volcanic flows gradually smoothed parts of the surrounding landscape, but the scars of the collision never disappeared. Unlike Earth, Mercury has almost no atmosphere and no weather. There is no rain to erode the mountains, no wind to carry away dust, no oceans to reshape the terrain. As a result, the Caloris Basin has remained visible for billions of years. It is a fossilized memory of a catastrophic moment in Mercury's past. Yet despite the basin's enormous size, early astronomers had no idea it existed. Even when Mariner 10 flew past Mercury in the 1970s, scientists could only see part of the basin. Because of the spacecraft's flight path, the Sun was positioned directly overhead when the photos were taken. This lighting made it difficult to see the full depth and structure of the crater. Many of the basin's features were hidden by harsh shadows and glare. For decades, the true scale of the Caloris Basin remained uncertain. Scientists suspected it was enormous, but they did not yet know just how complex its structure really was. Then, more than 30 years later, a new spacecraft arrived at Mercury. This mission would finally reveal the basin in stunning detail. The spacecraft was called Messenger. Launched by NASA in 2004, Messenger took a long and complicated path through the solar system, using gravity assists from Earth, Venus, and Mercury itself. After traveling more than 7 billion kilometers, the spacecraft finally entered orbit around Mercury in 2011. For the first time in history, humanity had a satellite circling the smallest planet. And when Messenger began mapping Mercury's surface, the Caloris Basin revealed secrets no one expected. Because the basin was not just an enormous crater, it was something far more complex. Hidden beneath its surface were clues that Mercury had once been far more geologically active than scientists ever imagined, and the Caloris Basin had played a crucial role in shaping that ancient world. For decades after the first discovery of the Caloris Basin, scientists were left with more questions than answers. The images sent back by Mariner 10 in the 1970s had revealed something enormous on Mercury's surface, a vast circular structure surrounded by rugged mountains and fractured terrain. But the spacecraft had only captured part of the planet, leaving huge areas unexplored. The full story of the Caloris Basin remained hidden. Then, in 2011, a new spacecraft arrived at Mercury. After a journey lasting more than 6 years and involving multiple gravity assists around Earth, Venus, and Mercury itself, NASA's Messenger spacecraft finally entered orbit around the smallest planet in the solar system. For the first time in human history, a spacecraft would remain around Mercury long enough to map the entire planet. And what Messenger discovered changed everything scientists thought they knew about the Caloris Basin. As the spacecraft began scanning the surface with high-resolution cameras and instruments, it slowly built a detailed map of Mercury's geology. Day after day, orbit after orbit, the planet revealed its ancient secrets. When Messenger finally captured the full view of the Caloris Basin, scientists were stunned. The basin was even larger and more complex than anyone had imagined. Stretching roughly 1,550 kilometers across, it ranked among the largest known impact basins in the solar system. Only a few craters on the Moon and Mars rivaled its scale. But size alone was not the most surprising discovery. Inside the basin, the terrain looked very different from the rugged mountainous rim that surrounded it. Instead of chaotic debris and broken rock, the interior was filled with relatively smooth plains. These plains appeared younger than the surrounding terrain, which raised an important question. If the Caloris Basin formed during one of the earliest and most violent periods of the solar system, why did the inside look smoother and less cratered than the outside? The answer pointed toward something unexpected: volcanic activity. Scientists began to realize that after the impact formed the Caloris Basin, molten rock from Mercury's interior likely rose through fractures in the crust. The enormous collision had cracked the planet's outer layers, creating pathways for magma to reach the surface. Over time, lava flooded the basin floor. Just as volcanic eruptions on Earth can cover landscapes with molten rock, ancient lava flows gradually filled large parts of the basin. When the lava cooled, it created the smooth plains that scientists see today. These volcanic plains tell us something remarkable about Mercury. For a long time, scientists believed Mercury was a geologically dead world, one that cooled quickly after formation and never experienced much internal activity. But the Caloris Basin tells a different story. It suggests that Mercury once had enough internal heat to drive massive volcanic eruptions. And those eruptions may have continued for hundreds of millions of years after the original impact. Messenger's instruments also revealed networks of wrinkle ridges crossing the basin floor. These ridges form when a planet's crust compresses and buckles. On Earth, similar features can appear in tectonic environments where the surface is pushed together. On Mercury, however, the ridges have a different cause. They likely formed as the planet slowly cooled over billions of years. As Mercury's enormous iron core cooled and contracted, the entire planet shrank slightly. That shrinking forced the crust to compress, and in the Caloris Basin, the relatively thin volcanic plains were squeezed into long, curved ridges stretching across the basin floor. Some of these ridges extend for hundreds of kilometers. They resemble frozen waves of stone crossing the ancient crater. Another discovery added to the mystery. The mountains forming the basin's outer ring were taller and more rugged than scientists initially expected. Some peaks rise more than 3 kilometers high, forming an enormous circular wall around the basin. These mountains were created during the chaotic collapse phase of the impact. When the asteroid struck Mercury billions of years ago, the explosion excavated a massive cavity in the crust. But the planet's gravity quickly began pulling material back inward. This collapse caused the edges of the crater to lift and buckle upward, forming the mountainous ring. In many ways, the Caloris Basin resembles enormous impact structures on the Moon, such as the Oriental Basin. Both features formed through similar processes. Yet Mercury's basin is unique in one important way. The extreme conditions of the inner solar system may have influenced how the basin evolved. Because Mercury is so close to the Sun, its surface experiences enormous temperature swings. During the day, the ground can reach 430 degrees Celsius. At night, it plunges to minus 180 degrees Celsius. Over billions of years, these extreme cycles of heating and cooling may have slowly reshaped parts of the basin's terrain. Rocks expand in the heat and contract in the cold. Repeated over millions of years, this process can gradually fracture and weaken the surface. Even so, the Caloris Basin remains remarkably well preserved. Unlike Earth, Mercury has almost no atmosphere. There is no rain to erode mountains, no rivers to carve valleys, no windstorms to move sand across the surface. Without these forces, geological features can remain almost unchanged for billions of years. This is why the scars of ancient impacts remain so clearly visible. Every crater, ridge, and fracture acts like a frozen record of the solar system's violent past. And the Caloris Basin is one of the most dramatic records of all. Yet perhaps the most intriguing discovery related to the basin lies far from its center, thousands of kilometers away on the opposite side of Mercury. Earlier, scientists studying Mariner 10 images had noticed a strange landscape called the Weird Terrain. This region looks completely different from the rest of the planet. Instead of smooth plains or typical craters, the surface appears twisted and shattered. Ridges intersect at odd angles. Hills and valleys form chaotic patterns. The ground seems as though it has been violently churned. At first, scientists had no explanation for this bizarre terrain. But once the full size and power of the Caloris impact became clear, a theory began to make sense. When the asteroid struck Mercury and created the Caloris Basin, the shockwaves traveled through the planet's interior. Those waves eventually reached the opposite side of the world. There, the seismic energy focused into one region. The result was the Weird Terrain. In effect, the Caloris impact shook the entire planet so violently that the crust on the far side collapsed into chaotic formations. If this theory is correct, it means the Caloris Basin did more than create a massive crater. It reshaped Mercury globally. Very few impact events in the solar system are known to have effects on this scale. Even the asteroid that ended the age of dinosaurs on Earth, forming the Chicxulub crater, did not fracture the entire planet. But Mercury is smaller, and its crust is thinner. The Caloris impact may have sent seismic waves powerful enough to reverberate through the entire world. This realization changed how scientists think about Mercury. Rather than being a quiet, inactive planet from the beginning, Mercury likely experienced periods of dramatic geological activity. Impacts, volcanic eruptions, and planetary contraction all shaped its surface. And the Caloris Basin sits at the center of that story. But despite everything we have learned, many mysteries remain. Scientists still debate the exact size of the object that struck Mercury. They also continue to study how the impact may have influenced Mercury's internal structure. Some researchers even wonder whether collisions like this one helped shape Mercury's unusually large metallic core. In other words, the Caloris Basin may not just be a crater. It could be a clue to the deeper history of the planet itself. And as scientists continue studying data from MESSENGER and future missions to Mercury, this enormous scar may reveal even more secrets about the violent birth of our solar system. When the asteroid struck Mercury and carved out the Caloris Basin, the damage did not end at the crater's edge. What followed was something far more extraordinary, because the impact did not just reshape a region, it shook the entire planet. To understand this, imagine Mercury not as a solid, unchanging rock, but as a layered world, a thin crust on the outside, beneath it a mantle, and at the center an enormous metallic core made mostly of iron. When the asteroid hit, the energy released did not stay on the surface. It moved inward. The collision generated powerful seismic waves, similar to the waves produced during earthquakes on Earth, but far more intense. These waves traveled through Mercury's crust and deep into its interior. And because Mercury is relatively small, those waves did not weaken as quickly as they would on a larger planet like Earth. Instead, they continued moving, faster than any human-made explosion, faster than sound could travel through rock. They spread out in every direction from the point of impact, across the crust, through the mantle, and even through the massive iron core at the planet's center. For a brief moment in Mercury's history, the entire planet was vibrating, not on the surface, but internally, like a bell struck with unimaginable force. As these seismic waves traveled, they carried enormous energy. They fractured rock. They destabilized the crust. They pushed and pulled the material inside Mercury in ways that had likely never happened before. And then, after racing across the planet, something remarkable occurred. The waves reached the opposite side. But they didn't simply pass through, they converged. Because Mercury is spherical, waves traveling from a single point will eventually meet again on the far side. And when they meet, their energy combines, it intensifies, it focuses into one region. On Mercury, that region became one of the strangest landscapes in the entire solar system. The weird terrain. When scientists first saw this area in images from Mariner 10, they were confused. The terrain looked completely different from everything else on the planet. Instead of normal craters or smooth plains, the surface appeared shattered. Hills rose at odd angles. Valleys cut through the land in unpredictable patterns. The ground looked twisted, broken, and chaotic. At first, there was no clear explanation. But once the scale of the Caloris impact was understood, the pieces began to fit together. The seismic waves from the impact had traveled through Mercury's interior and slammed into the far side of the planet. When those waves arrived, they released their energy all at once. The result was a violent upheaval of the surface. The crust buckled. Rocks were lifted and dropped. Entire sections of terrain collapsed into disordered formations. It was not a crater. It was not volcanic activity. It was something different, a kind of seismic explosion caused by energy traveling through the planet itself. The weird terrain became a permanent record of that event. Even today, billions of years later, the surface still shows the scars of those converging shockwaves. This phenomenon is extremely rare. Very few impacts in the solar system are powerful enough to affect a planet on a global scale. Most impacts create local damage, craters, ejecta, and fractures around the impact site. But the Caloris impact was different. It was so powerful that it sent energy across the entire world. And that tells us something important about Mercury. It tells us that the planet's interior is capable of transmitting energy efficiently. that its structure, its crust, mantle, and core, allowed those waves to travel without being completely absorbed or scattered. In other words, the Caloris Basin does not just reveal something about the surface. It reveals something about what lies beneath. Scientists studying these effects have used the basin to learn more about Mercury's internal composition. By analyzing how seismic waves likely traveled through the planet, they can estimate the properties of the mantle and core. And what they have found is fascinating. Mercury's interior is dominated by a massive metallic core, far larger than expected for a planet of its size. This core likely played a role in how the seismic waves moved. Metal conducts energy differently than rock. The presence of such a large iron core may have helped transmit the shockwaves more efficiently, allowing them to reach the opposite side with enough strength to disrupt the surface. But the story does not end with seismic waves, because the impact also triggered changes that unfolded over much longer periods of time. When the asteroid struck Mercury, it did more than fracture the crust. It heated the planet's interior. The energy released by the collision may have temporarily increased temperatures deep below the surface. That heat could have weakened the mantle. It could have created pockets of molten material. And it may have set the stage for volcanic activity that would occur millions of years later. In fact, some scientists believe that the Caloris impact helped trigger the volcanic flooding that filled the basin. The fractures created by the impact may have acted as pathways for magma to rise from below. Over time, this magma would erupt onto the surface, spreading across the basin floor. This means that the Caloris Basin is not just an impact crater. It is also a volcanic feature, a place where two powerful processes, collision and eruption, combined to shape the landscape. And then there is the question of Mercury's shape. Over billions of years, Mercury has been slowly shrinking. As its massive iron core cools, it contracts. This contraction pulls the crust inward, creating features known as lobate scarps, long, curved cliffs that can stretch for hundreds of kilometers. Some of these scarps cut across the Caloris Basin itself, which means they formed after the impact. This tells us that the basin has existed for a very long time, long enough for the entire planet to cool and contract around it. In a way, the Caloris Basin has witnessed multiple stages of Mercury's history. First, the violent impact that created it. Then, the volcanic eruptions that reshaped its interior. And finally, the slow contraction of the planet as it cooled. Each stage left its mark. Each stage added another layer to the story. And together, they reveal a world far more dynamic than it first appears. Mercury may look like a silent, cratered rock, but beneath that surface lies a history of immense energy, a history of collisions that shook the entire planet, a history of internal forces that reshaped its crust. And at the center of that history is the Caloris Basin, a scar so large, so powerful, that its effects can be seen on both sides of the world. When scientists first saw the Caloris Basin, they believed they were looking at nothing more than the scar of an ancient impact, a gigantic crater carved into Mercury's surface billions of years ago. But as new data arrived from spacecraft missions, especially from NASA's Messenger, a more complex story began to emerge. Because the Caloris Basin was not just shaped by a collision, It was also shaped by fire from within the planet itself. After the asteroid struck Mercury and blasted out the enormous cavity that became the Caloris Basin, the planet's crust did not simply settle back into place and remain frozen in time. The impact had cracked the crust deeply, and those fractures reached far below the surface. Imagine dropping a massive rock into a frozen lake. The ice doesn't just break where the rock lands. Cracks spread outward across the surface. On Mercury, something similar happened, but on a planetary scale. The collision fractured the crust over thousands of kilometers, and those fractures created pathways that connected Mercury's deep interior to its surface. Deep beneath the crust, the planet still held enormous heat. Despite its small size, Mercury was not completely solid. Its interior contained molten material, magma slowly moving beneath the crust. Under normal conditions, this magma might remain trapped deep underground, but the Caloris impact changed that. The cracks caused by the collision allowed molten rock to begin rising upward, slowly at first, then in bursts. Eventually, magma reached the surface, and when it did, it erupted. Volcanic lava began flowing across the floor of the Caloris Basin. These eruptions were not like the explosive volcanoes seen on Earth. Mercury lacks an atmosphere and contains very little gas trapped inside its magma. Without gas pressure, eruptions would have been relatively calm, similar to the lava flows seen in Hawaii. But calm does not mean small. The lava flows on Mercury could have covered enormous distances. Molten rock poured into the basin, spreading outward like thick liquid across the ancient crater floor. Over time, layer after layer of lava accumulated. These volcanic floods gradually buried much of the original impact damage. Deep cracks disappeared beneath cooled rock. Smaller craters were filled in. The basin floor became smoother and more level. Today, when scientists examine images of the Caloris Basin, they can clearly see this difference. The interior plains appear smoother and less heavily cratered than the surrounding terrain. That tells us something important. The volcanic activity occurred after the impact, and it continued long enough to reshape large portions of the basin. In fact, some estimates suggest that volcanic eruptions in the Caloris region may have continued for hundreds of millions of years, which is remarkable for a planet that many once believed to be geologically dead. Messenger's instruments provided additional clues. Using spectrometers and imaging systems, the spacecraft measured the chemical composition of Mercury's surface. The results showed that the plains inside the basin contain different materials than the surrounding crust. These materials are consistent with volcanic lava flows. The plains are rich in elements like magnesium and sulfur, which are common in volcanic rock. This confirmed what scientists had begun to suspect. The Caloris Basin is not just an impact structure. It is also one of Mercury's largest volcanic provinces, and that volcanic activity reveals something surprising about Mercury's interior. For many years, scientists assumed Mercury cooled very quickly after forming. Because the planet is small, it should have lost its internal heat faster than larger planets like Earth or Venus. But the evidence from Caloris suggests that Mercury remained internally active much longer than expected. The heat trapped inside the planet was enough to drive volcanic eruptions long after the original impact, and those eruptions may have played a role in shaping the broader landscape surrounding the basin. Outside the Caloris Basin, scientists have identified enormous lava plains stretching across Mercury's surface. These plains resemble the mare regions on the Moon, where ancient lava once flooded huge impact basins. But Mercury's volcanic plains appear even more extensive. In some regions, they cover areas larger than entire countries on Earth. Some of these plains may be connected to the Caloris Basin itself. The massive fractures created by the impact could have extended far beyond the crater's rim, allowing magma to reach the surface in distant regions. In other words, the Caloris impact may have triggered volcanic activity across a much wider area of Mercury. Another clue comes from unusual features found within the basin. Scientists have identified structures known as volcanic vents. These vents appear as irregular pits or depressions in the surface. They may mark the locations where magma once erupted onto the basin floor. Unlike typical impact craters, these pits have steep sides and lack the raised rims formed by collisions. Instead, they appear to have formed when underground magma chambers collapsed after lava was released. These volcanic vents provide further evidence that the Caloris Basin experienced prolonged geological activity. Yet, despite all this activity, Mercury eventually cooled. As billions of years passed, the planet's interior slowly lost heat. Volcanic eruptions became less frequent. Magma deep inside the planet solidified, and the once active pathways created by the Caloris impact gradually closed. The basin entered a new phase of its history, one defined not by fire, but by silence. Without volcanic eruptions or atmospheric weathering, the surface of Mercury changed very little over time. Small asteroids continued to strike the basin floor. Each new impact added another crater, but the overall shape of the Caloris Basin remained largely unchanged. The lava plains hardened into stone, the mountainous rim remained standing, and the ancient scar endured. Today, when scientists look at the Caloris Basin, they see more than just a crater. They see a record of multiple stages of planetary evolution. First came the catastrophic impact that created the basin, then the volcanic eruptions that filled it, and finally the slow cooling of Mercury itself. Each stage tells us something about the history of the smallest planet in the solar system. But perhaps the most important lesson from Caloris is this: even a planet that appears quiet and lifeless can have a dramatic and violent past. Mercury may look like a simple gray world, but beneath its surface lies a story of immense forces. Asteroids powerful enough to shake the entire planet, volcanoes capable of flooding enormous basins with molten rock, and geological changes that unfolded over billions of years. The Caloris Basin is not just a crater, it is a window into Mercury's fiery past. And it reminds us that even the smallest planets can experience events powerful enough to reshape entire worlds. Even after the asteroid struck Mercury and the volcanic eruptions filled the Caloris Basin with molten rock, the story of the basin was not finished. Because Mercury itself was still changing, slowly, quietly, but on a planetary scale. Unlike Earth, Mercury does not have moving tectonic plates. There are no drifting continents, no spreading ocean floors, and no massive mountain chains created by colliding land masses. For a long time, scientists believed Mercury was geologically inactive, a frozen world whose interior had cooled long ago. But when spacecraft began studying the planet closely, they discovered something surprising. Mercury is shrinking, very slowly, but unmistakably. This shrinking is happening because Mercury's enormous iron core is gradually cooling. Deep inside the planet lies a metallic core that makes up most of Mercury's interior. When Mercury first formed billions of years ago, that core was extremely hot, likely molten throughout much of its depth. Over time, however, the core began to lose heat. As metal cools, it contracts, and because Mercury's core is so large, even a small amount of cooling can cause the entire planet to shrink. Scientists estimate that Mercury's radius has decreased by several kilometers since the planet first formed. That might not sound like much, but for a planetary body, it represents an enormous structural change. Imagine a metal ball slowly shrinking while the thin shell around it tries to adjust. The outer crust has no choice but to compress, and when rock is squeezed, it fractures. The result is the formation of dramatic geological structures known as lobate scarps. These features are essentially giant cliffs that form when sections of the crust are pushed upward as the planet contracts. Some of these scarps are truly enormous. They can stretch for hundreds of kilometers across the surface, and they can rise more than a kilometer high. From orbit, they look like massive wrinkles across Mercury's landscape, like the surface of a drying apple. One of the most fascinating discoveries made by the Messenger spacecraft was that several of these scarps cut directly across the Caloris Basin. This observation revealed something important. It means that the Caloris Basin existed before Mercury began shrinking significantly. The impact that formed the basin happened early in Mercury's history. But the contraction of the planet continued long afterward. In other words, the Caloris Basin has witnessed billions of years of Mercury's evolution. First, the massive impact, then volcanic flooding, and later, the slow compression of the planet itself. In some parts of the basin, the contraction of Mercury's crust created long ridges across the volcanic plains. These ridges, known as wrinkle ridges, formed as the surface was squeezed together. They are smaller than the giant scarps found elsewhere on Mercury, but they still stretch for many kilometers. If you could stand on the surface of the Caloris Basin, you would see these ridges rising gently across the plains. They resemble frozen waves of rock, evidence that the ground itself was once compressed. But perhaps the most dramatic scarps occur near the basin's outer edges. Here, enormous cliffs mark places where the crust was pushed upward by the shrinking planet. Some of these cliffs cut across ancient craters and volcanic plains alike, which means they formed after those features. They are among the youngest large geological structures on Mercury. This tells scientists something remarkable. Mercury's contraction may still be happening today, not dramatically, not violently, but gradually. The planet continues to cool, and as it cools, it continues to shrink. This slow transformation has reshaped the Caloris Basin over billions of years. What began as a violent crater has gradually become a complex geological landscape. A place where multiple forces have left their mark: impact, volcanism, and planetary contraction. But the shrinking of Mercury has another consequence, one that scientists did not fully appreciate until recently. The contraction of the planet may have influenced Mercury's magnetic field. Unlike most small, rocky bodies, Mercury actually possesses a global magnetic field. It is weak compared to Earth's, but it exists, and it originates from the movement of molten metal inside the planet's core. As Mercury's core slowly cools and solidifies, the dynamics of that molten metal change. This affects how the magnetic field is generated. Some scientists believe that the Caloris impact itself may have influenced Mercury's magnetic field in the distant past. The enormous energy released during the collision could have temporarily disturbed the planet's internal structure. It may even have altered how heat moved through the core. Although this idea is still being studied, it highlights how interconnected planetary processes can be. A single massive impact can trigger a chain of events that affects the entire planet. Surface geology, volcanic activity, internal heat flow, even magnetic fields. And the Caloris Basin stands at the center of one of the most dramatic examples of this process. Yet despite everything we have learned, many mysteries remain. For example, scientists still debate the exact size of the asteroid that created the basin. Estimates suggest it may have been between 80 and 150 kilometers wide. But the true size depends on the speed of the impact and the angle at which the asteroid struck. A faster or steeper collision would produce a larger basin. Another mystery involves the distribution of volcanic plains around the basin. Some areas appear heavily flooded with lava. Others remain rough and cratered. Why did magma emerge in some regions but not others? One possibility is that the impact fractured the crust unevenly. Some cracks may have reached deep enough to tap into molten rock. Others may have stopped before reaching magma reservoirs. Another question concerns the strange terrain on the opposite side of Mercury. While the shockwave theory remains the leading explanation, scientists continue to study whether other processes may also have contributed to the weird terrain. Future missions to Mercury may help answer these questions. In 2018, a new mission called Bepi Colombo, developed by the European Space Agency and the Japan Aerospace Exploration Agency, began its journey toward Mercury. The spacecraft is expected to arrive in orbit around the planet in the coming years. With more advanced instruments than previous missions, Bepi Colombo will study Mercury's surface, interior, and magnetic field in greater detail. It may provide new insights into the Caloris Basin, new clues about the asteroid that created it, and perhaps new discoveries about Mercury's shrinking crust. Until then, the Caloris Basin remains one of the most powerful reminders of the solar system's violent past. A scar carved by an impact so immense that it shook an entire planet. A crater filled with ancient lava. A landscape reshaped by billions of years of planetary contraction. And a place where the story of Mercury continues to unfold. Because even now, the smallest planet in our solar system is still slowly changing. Billions of years ago, long before life appeared on Earth, the inner solar system was a place of constant destruction. Planets were still forming. Vast clouds of debris drifted through space. Asteroids, protoplanets, and fragments left over from planetary formation were moving in unstable orbits around the young sun. Collisions were common. Sometimes small rocks struck planetary surfaces, leaving minor craters. Other times, the impacts were enormous, world-changing. The Caloris Basin on Mercury is evidence of one of those events, but one question has fascinated scientists for decades. What kind of object could create a crater over 1,500 kilometers wide? To answer that, researchers have studied both the basin itself and computer simulations of massive impacts. The results suggest that the object responsible for the Caloris Basin was no ordinary asteroid. It was likely a body between 80 and 150 kilometers in diameter. To put that into perspective, such an object would be larger than many mountain ranges on Earth. If placed on our planet, it would stretch across entire regions or even countries. And that massive object was moving at incredible speed. Because Mercury orbits very close to the Sun, objects traveling through its region of space move much faster than asteroids farther out. Typical impact speeds near Mercury can exceed 40 kilometers per second. That is about 150,000 kilometers per hour. At such speeds, the kinetic energy of even a moderately sized asteroid becomes enormous. When scientists calculate the energy released during the Caloris impact, the numbers become almost impossible to comprehend. The collision likely released energy equivalent to millions of nuclear bombs detonating simultaneously. Temperatures at the impact site would have soared high enough to melt rock instantly. Vast amounts of Mercury's crust were vaporized. The asteroid itself disappeared completely, transformed into molten debris and gas. For a brief moment, the region around the impact would have looked like a glowing inferno. Shockwaves blasted outward across the surface, molten rock erupted upward, and fragments of Mercury's crust were thrown thousands of kilometers across the planet. Some debris likely escaped Mercury's weak gravity entirely, but most of it fell back to the surface. When the ejecta returned, it formed a layer of scattered debris surrounding the basin. Scientists call this material the ejecta blanket. Around the Caloris Basin, this ejecta layer extends for hundreds of kilometers. It is made of rock that was blasted out during the explosion and then fell back to the surface. In some areas, the ejecta formed strange radial patterns, lines of debris stretching outward from the crater. These patterns reveal how the explosion unfolded. Material closer to the impact site was thrown higher and farther. Material at greater distances landed earlier. Together, they created the complex landscape surrounding the basin. But the impact produced another extraordinary effect. When the asteroid struck Mercury, the force of the collision compressed the crust beneath it. The rock was pushed downward with enormous pressure. Then, as the energy dissipated, the crushed material rebounded upward. This rebound created the central structures seen inside many large impact basins. Although volcanic lava later flooded much of the Caloris Basin's interior, scientists believe the original crater may have contained a central uplift, an enormous mound of rock pushed upward by the rebound. On Earth and the Moon, similar structures exist inside large craters. They form when the surface briefly behaves like a liquid under extreme pressure. The ground sinks, rebounds, and reshapes itself within minutes. These processes happen so quickly that the landscape forms almost instantly. The entire Caloris Basin may have taken less than an hour to reach its basic shape, but the consequences of that single moment lasted billions of years. Because the Caloris impact occurred during a time known as the Late Heavy Bombardment. This was a period roughly 4 billion years ago when the inner solar system experienced a dramatic increase in asteroid impacts. Scientists believe that changes in the orbits of the giant planets, especially Jupiter and Saturn, destabilized large numbers of asteroids. These asteroids were scattered throughout the solar system. Many of them struck the inner planets. The Moon, Mars, Venus, Earth, and Mercury were all bombarded by these impacts. On the Moon, the late heavy bombardment created enormous basins such as Imbrium and Orientale. On Earth, many similar impacts likely occurred. But because Earth has oceans, weather, and tectonic activity, most of those ancient scars have been erased. Mercury and the Moon, however, preserve those ancient records. Their surfaces remain largely unchanged for billions of years. That is why the Caloris Basin still exists today. It is a surviving witness to the violent era when the solar system was young. Yet the Caloris impact may have had consequences far beyond the basin itself. Some scientists have proposed that impacts of this scale could influence a planet's internal structure. In Mercury's case, the enormous energy released may have altered how heat moved through the mantle. It could have triggered volcanic eruptions. It may even have affected the dynamics of Mercury's massive iron core. These possibilities are still being studied, but they highlight something important. Large impacts do not simply leave craters. They can reshape entire worlds. And the Caloris Basin is among the best examples of that process. Yet, despite its enormous size, the basin remained hidden from humanity for most of history. Mercury's proximity to the Sun made it extremely difficult to observe from Earth. For centuries, astronomers could only see Mercury as a bright point of light. Even with powerful telescopes, the planet appeared small and blurred by sunlight. It was not until spacecraft visited Mercury that scientists finally saw the Caloris Basin in detail, and when they did, they realized something remarkable. The basin was not just large, it was one of the largest impact structures in the entire solar system. Its size places it among the most powerful collisions known on any planetary surface. And yet, Mercury survived. The planet did not break apart. It did not lose its orbit. Instead, it absorbed the impact and continued evolving. This resilience tells us something important about Mercury's structure. Despite its small size, the planet is incredibly dense and compact. Its enormous iron core gives it remarkable internal strength. Without that core, the Caloris impact might have had far more destructive consequences. Some scientists even speculate that if Mercury had been less dense, or if the asteroid had been slightly larger, the collision might have shattered the planet's crust entirely. Instead, Mercury endured. The basin formed, the planet shook, volcanoes erupted, and over billions of years, the landscape slowly stabilized. Today, the Caloris Basin stands as one of the most dramatic geological features in the solar system, a scar created by an asteroid that changed Mercury forever. But the basin also raises a deeper question. If such a massive impact happened once, could it happen again? And if it did, what would it mean for the future of planets across the solar system? Because the forces that shaped Mercury billions of years ago have not completely disappeared. Asteroids still roam the solar system, and somewhere in the darkness of space, objects large enough to reshape worlds are still drifting silently between the planets. To To truly understand why the Caloris Basin exists on Mercury, we have to step even further back in time, back to one of the most chaotic chapters in the history of the solar system. A time when planets were not yet peaceful worlds, a time when collisions were constant, a time known as the Late Heavy Bombardment. Roughly 4.1 to 3.8 billion years ago, the inner solar system experienced a dramatic spike in asteroid impacts. During this period, enormous numbers of rocky bodies were flung inward toward the Sun, striking the young planets again and again. Mercury, Venus, Earth, Mars, and the Moon all endured these violent collisions. The evidence for this era can still be seen today. On the Moon, many of the largest basins, such as Imbrium, Serenitatis, and Orientale, formed during this period. On Mars, ancient impact basins cover large portions of the southern hemisphere. And on Mercury, the Caloris Basin stands as one of the most dramatic scars from that time. But where did all these asteroids come from? The answer likely lies far beyond the inner solar system. Billions of years ago, the giant planets, Jupiter, Saturn, Uranus, and Neptune, did not occupy the stable orbits they have today. Instead, they were slowly migrating. Gravitational interactions between these massive planets caused their orbits to shift over time. As they moved, they disturbed vast populations of icy and rocky objects located in the outer solar system. These objects were scattered inward like cosmic debris from a planetary slingshot. Many of them ended up crossing the orbits of the inner planets. The result was a prolonged era of intense impacts. Asteroids tens of kilometers wide crashed into planetary surfaces. Some collisions created craters hundreds or even thousands of kilometers across. Others may have temporarily melted entire regions of planetary crust. For Mercury, this period was particularly destructive. Because of its proximity to the Sun, Mercury already moved through a region of space where objects traveled at extremely high speeds. When asteroids struck Mercury during the Late Heavy Bombardment, the impacts were especially energetic. A rock traveling 40 or 50 kilometers per second carries enormous kinetic energy. Even a modest asteroid can produce a crater dozens of kilometers wide. But the largest objects created features on a completely different scale. The Caloris Basin was one of those features. It likely formed near the peak of the Late Heavy Bombardment, when massive asteroids were still common. The asteroid that struck Mercury may have been one of the last giant impactors to collide with the planet. By the time the bombardment began to decline, most of the large debris in the inner solar system had either been absorbed by planets or ejected into interplanetary space. The rate of impacts gradually decreased. Planetary surfaces became more stable. But the scars from that violent era remained. On Mercury, those scars are everywhere. If you look at high-resolution images of the planet's surface, you will see countless craters overlapping one another. Some craters cut into older ones. Others are partially buried by lava flows. Together, they create a layered record of billions of years of impacts. Scientists can estimate the relative ages of different regions by counting how many craters they contain. Surfaces with many craters are generally older. Surfaces with fewer craters are younger. Using this technique, researchers discover something fascinating about the Caloris Basin. The basin itself is extremely ancient, but the volcanic plains inside it are somewhat younger. This means the impact happened first. and volcanic activity reshaped the basin later. Beyond the basin's rim, the surrounding terrain shows signs of even older impacts. These regions may date back to the earliest stages of Mercury's history. Some craters there may have formed more than 4 billion years ago. The Caloris Basin, therefore, sits within a landscape that has been shaped by impacts for almost the entire lifetime of the solar system. Yet, despite the immense number of craters, the basin still stands out. Its sheer size makes it impossible to miss. Even from space, its circular outline dominates the surrounding terrain. But the late heavy bombardment raises another intriguing question. If Mercury experienced so many massive impacts, why did the planet survive? Why wasn't it shattered completely? The answer lies partly in Mercury's structure. As we discussed earlier, Mercury contains an enormous iron core. This core accounts for most of the planet's mass. Iron is dense and strong. It provides structural stability. During large impacts, the core absorbs and distributes energy more effectively than a purely rocky interior would. In other words, Mercury is tougher than it looks. Another factor is the size of the impactors. Although the asteroid that created the Caloris Basin was extremely large, it was not large enough to destroy the planet entirely. Planetary destruction typically requires collisions between objects of similar size, events that occurred during the very earliest stages of planetary formation. By the time the late heavy bombardment occurred, most of the largest bodies in the solar system had already formed. The remaining asteroids were dangerous, but not catastrophic enough to break apart entire planets. Still, the Caloris impact came close to the upper limits of what Mercury could endure. If the asteroid had been twice as large, or if it had struck at a different angle, the outcome might have been far more destructive. Some scientists even speculate that Mercury may have experienced other enormous impacts earlier in its history, events that stripped away much of its outer mantle. This could help explain why the planet has such a large metallic core, compared to its thin rocky crust. If true, Mercury may have survived multiple planet-altering collisions, each one shaping the planet we see today. But the late heavy bombardment eventually came to an end. As the giant planets settled into their current orbits, the supply of wandering asteroids decreased. The inner solar system became quieter. Impacts still occur today, but they are far less frequent. Large asteroids capable of forming giant basins are extremely rare. The violent era that created the Caloris Basin is long over, yet the evidence remains frozen in Mercury's landscape. Every crater, every ridge, every fractured plane. Each one is a reminder of a time when the solar system was far more dangerous than it is today. And among all those ancient scars, the Caloris Basin stands as one of the most powerful witnesses to that history. A record of a moment when a single asteroid reshaped an entire world. But the basin also reminds us of something else. Even in a quiet solar system, even after billions of years, the forces that shaped Mercury are still out there. Asteroids still drift between the planets. Most are small. Most will never collide with anything. But somewhere in the vast darkness of space, objects large enough to carve new basins still exist, waiting, moving silently through the solar system. Just as the asteroid that created the Caloris Basin once did. For thousands of years, Mercury remained one of the most mysterious worlds in the sky. It was visible to ancient astronomers, appearing briefly at dawn or sunset. But its proximity to the Sun made detailed observations nearly impossible. Even powerful telescopes struggled to reveal much about the planet's surface. Mercury always appeared small, washed out by sunlight, and difficult to study. Because of this, the Caloris Basin, the largest scar on Mercury, remained completely unknown to humanity until the space age. Everything changed in the 1970s. In 1973, NASA launched a spacecraft called Mariner 10. Its mission was ambitious: to explore both Venus and Mercury using a new technique called a gravitational assist. By passing close to Venus, the spacecraft would gain speed and redirect its path toward Mercury. This method allowed Mariner 10 to become the first spacecraft ever to reach the innermost planet. When it arrived in 1974, the spacecraft flew past Mercury and began taking images. The pictures that returned to Earth were astonishing. For the first time, humanity saw Mercury's surface in detail. It looked surprisingly similar to the Moon, gray, cratered, and ancient. Vast impact scars covered the planet. Some craters overlapped others, creating complex layers of geological history. But among those craters was something enormous, a gigantic circular structure that dwarfed everything around it. This was the Caloris Basin. Even in the early images, scientists could see that the basin was immense. A vast ring of mountains surrounded the structure, and the interior appeared smoother than the surrounding terrain. But there was a problem. Mariner 10's trajectory allowed it to photograph only about 45% of Mercury's surface. Large portions of the planet remained hidden in darkness or were never seen by the spacecraft. Even worse, the lighting conditions during the flybys were not ideal. The sun was positioned almost directly overhead when many of the images were taken. Without strong shadows to reveal the shape of the terrain, the true depth and structure of the basin were difficult to interpret. Scientists knew the Caloris Basin was massive, but they did not yet know exactly how massive, and they had only a partial view of the surrounding landscape. For decades, the basin remained a mystery. Researchers studied the available images, trying to estimate the basin's diameter and understand how it formed. But without a complete map of Mercury's surface, many questions remained unanswered. Then, in 2004, NASA launched another mission. This spacecraft was called MESSENGER, short for Mercury Surface, Space Environment, Geochemistry and Ranging. Unlike Mariner 10, which only flew past Mercury, MESSENGER was designed to enter orbit around the planet and study it for an extended period of time. Reaching Mercury, however, was extremely difficult. Because the planet lies so close to the Sun, a spacecraft approaching it must slow down significantly to avoid being pulled into the Sun's gravity. To accomplish this, MESSENGER performed a series of gravitational assists around Earth, Venus, and Mercury itself. The journey lasted nearly 7 years. Finally, in March 2011, the spacecraft successfully entered orbit around Mercury. For the first time in human history, a satellite was circling the smallest planet in the solar system, and almost immediately, Mercury began revealing its secrets. MESSENGER's cameras captured images of the planet with far greater resolution than anything previously obtained. Its instruments measured the chemical composition of the surface, mapped the planet's gravity field, and studied Mercury's magnetic environment. As the spacecraft orbited Mercury again and again, it gradually built a complete map of the entire planet. And when scientists finally saw the full Caloris Basin, they realized something remarkable. The basin was even larger and more complex than previously believed. Measuring roughly 1,550 kilometers across, it ranks among the largest impact basins in the solar system. The rim of the basin forms a ring of mountains that rise several kilometers above the surrounding terrain. These mountains were created when the crust collapsed and rebounded after the enormous impact. Inside the basin, Messenger discovered smooth volcanic plains covering much of the floor. These plains are made of ancient lava flows that erupted long after the original impact. But perhaps the most fascinating discoveries came from the basin's interior features. Messenger identified numerous volcanic vents, fractures, and wrinkle ridges scattered across the plains. Some of these vents appear as irregular depressions in the surface. They may mark the locations where magma once erupted onto the basin floor. Other regions contain networks of ridges, formed as the planet slowly cooled and contracted. These ridges curve across the plains like frozen waves. Together, they reveal that the basin experienced a long and complex geological history. The impact that formed Caloris was only the beginning. Volcanic eruptions, tectonic compression, and smaller asteroid impacts all reshaped the basin over billions of years. But Messenger also made another surprising discovery. Near the center of the basin, scientists found unusual features called hollows. These hollows are shallow, irregular depressions scattered across Mercury's surface. They appear bright in spacecraft images and lack the raised rims typical of impact craters. Scientists believe these hollows formed when volatile materials, substances that can easily vaporize, escaped from the surface. As these materials evaporated into space, the ground above them collapsed, leaving behind shallow pits. The presence of hollows suggests that Mercury's crust contains more volatile elements than scientists once expected. This discovery was surprising because Mercury formed very close to the Sun, where volatile materials were thought to be rare. Yet, the hollows prove that Mercury still holds chemical secrets beneath its surface. Another discovery involved the basin's gravity field. By carefully tracking the movement of Messenger as it orbited Mercury, scientists were able to measure subtle changes in the spacecraft's trajectory. These changes revealed variations in the planet's gravitational pull. The data showed that the Caloris Basin contains large amounts of dense material beneath its surface. This suggests that the impact may have excavated deep layers of Mercury's crust, exposing denser rock below. In some areas, the basin floor may even be thinner than surrounding regions. All of these discoveries have helped scientists better understand the violent processes that shaped Mercury. But the exploration of Mercury is not finished. In 2018, another mission began its journey toward the planet. This mission, called Bepicolombo, is a joint project between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA. Bepicolombo carries 2 orbiters equipped with advanced instruments designed to study Mercury's surface, interior, and magnetic field in unprecedented detail. When the spacecraft arrives in orbit later this decade, it will provide even more data about the Caloris Basin. Scientists hope to learn more about the asteroid that created the basin, the volcanic eruptions that filled it, and the strange geological features scattered across its surface. Every new mission adds another piece to the puzzle, and each new discovery reminds us that Mercury is far more complex than it once seemed. The Caloris Basin, once hidden from human eyes, has become one of the most important geological landmarks in the solar system, a scar formed in a moment of unimaginable violence, a landscape shaped by volcanic fire and planetary contraction, and a place that continues to reveal new secrets about the smallest and perhaps most mysterious planet orbiting our Sun. When we look at Mercury today, it appears quiet. A small gray planet orbiting silently around the Sun. No oceans, no clouds, no winds, no life. Just a barren world covered in craters. But beneath that quiet surface lies one of the most violent histories in the solar system. And nowhere is that history more visible than in the Caloris Basin. The basin is not just a crater. It is a timeline. A geological record carved into the surface of Mercury, preserving billions of years of planetary evolution. It begins with a moment of unimaginable violence. More than 4 billion years ago, during the chaotic early era of the solar system, a massive asteroid crossed Mercury's path. The collision that followed released energy equivalent to millions of nuclear explosions. Rock vaporized instantly. The crust shattered. Shockwaves rippled through the entire planet. In a matter of minutes, an enormous cavity formed over 1,500 kilometers wide. The Caloris Basin was born. But the impact did more than leave a hole in the surface. It shook Mercury from the inside. Seismic waves traveled through the planet's interior and converged on the opposite side of the world. There, the surface collapsed into a chaotic region now known as the Weird Terrain. It was as if the entire planet had been struck like a bell. Few impacts in the solar system are known to have effects on such a global scale, yet Mercury survived. The planet endured the collision and slowly began to recover. Over time, molten rock from deep within Mercury rose through fractures created by the impact. Volcanic eruptions flooded the basin floor with lava. These flows cooled and hardened into smooth plains, burying much of the original crater floor beneath layers of volcanic rock. The Caloris Basin transformed from a violent impact site into a vast volcanic landscape. But Mercury's story did not end there. As billions of years passed, the planet continued to cool. Its enormous iron core slowly lost heat, and as the core cooled, it contracted. That contraction caused the entire planet to shrink. The crust, unable to compress smoothly, fractured. Massive cliffs called lobite scarps formed across the surface. Some of these cliffs cut directly across the Caloris Basin itself. Evidence that the basin has witnessed multiple stages of Mercury's evolution: impact, volcanism, planetary contraction. Each event left its mark on the basin's landscape. Today, if we could stand on the rim of the Caloris Basin and look across its surface, we would see a world shaped by immense forces, towering mountain rings marking the edge of the original impact, smooth volcanic plains stretching across the basin floor, curving ridges formed by the slow compression of Mercury's crust, and scattered craters created by smaller asteroids that struck the basin long after its formation. Every feature tells a story. Every ridge and fracture reveals something about the planet's past. But perhaps the most remarkable thing about the Caloris Basin is how long it has survived. On Earth, features this ancient rarely remain intact. Our planet's surface is constantly reshaped by erosion, tectonic activity, and weather. Mountains rise and fall. Oceans open and close. Continents drift across the globe. Over billions of years, most ancient impact craters disappear. But Mercury is different. With almost no atmosphere and no active plate tectonics, its surface changes very slowly. The scars of ancient impacts remain visible for billions of years, which means the Caloris Basin is essentially a fossil of the early solar system, a frozen memory of a time when planets were still forming and collisions were common. And studying that fossil helps scientists answer deeper questions about how planets evolve, about how impacts shape planetary surfaces, about how internal heat and volcanic activity transform landscapes. The Caloris Basin also reminds us how fragile planetary worlds can be. A single asteroid, large enough and fast enough, can reshape an entire planet. The asteroid that struck Mercury changed the planet forever. Yet events like this were once common. During the early history of the solar system, impacts like the one that created Caloris happened many times. Some scientists believe Earth itself experienced collisions just as powerful. One such collision may have formed the Moon. Another asteroid, much smaller but still devastating, struck Earth 66 million years ago, contributing to the extinction of the dinosaurs. Compared to those events, the Caloris impact was far larger, and yet Mercury endured. Today, the basin remains one of the most striking geological features in the solar system. It is visible even from orbit as a vast circular scar across Mercury's equatorial region. Spacecraft like Mariner 10 and Messenger have mapped its surface in incredible detail. And future missions like Bepi Colombo will continue studying this ancient structure. Each mission reveals new clues, new measurements of Mercury's gravity field, new images of volcanic plains and fracture systems, new data about the planet's interior. Together, these discoveries help scientists piece together the history of Mercury, a history written in rock. But the Caloris Basin is more than just a scientific curiosity. It is a reminder of the forces that shaped our cosmic neighborhood. When we look at Mercury, we are not just seeing a distant planet. We are seeing the aftermath of billions of years of cosmic violence, a world battered by asteroids, shaken by planetary shockwaves, reshaped by fire from its own interior, and somehow still orbiting the Sun. The Caloris Basin stands as one of the greatest scars left by that violence, a wound that never healed, a monument to one of the most powerful impacts in the solar system, and a window into the turbulent birth of the planets themselves. Because long before Earth became a place of oceans and life, worlds like Mercury were enduring collisions powerful enough to reshape entire planets, and the Caloris Basin is the silent witness to one of those moments. A moment when an asteroid struck with unimaginable force and forever changed the smallest planet in our solar system.